Okay. Okay, so let's start. I'm gonna write one of the first question, and I would give you like 5 minutes or so, and then I'm gonna solve it. So the first question is: we have a continuous function f from an interval, say 0 to 1, to itself. Then this function is a continuous function. And we want to show this function has a fixed point. F has a fixed point, which means there exists a point x in this interval from 0 to 1, such that f of x equals x. We want to prove that. So think about it for a few minutes, and if you have an answer, you can just tell me. Yeah, you can unmute yourself, tell me what do you think, and then I'm gonna solve it. Yeah, this is being recorded. Well, yeah. I'm gonna upload it on Blackboard. Okay. Any answer? You can If you can unmute yourself, you can answer. And if not, you can raise your hand and I would unmute you. Okay, see, we can look at the graph of this function. This is a function from, well, this is from the interval 0 to 1 to interval 0 to 1, right? And the graph of a function would look like something like this. This is a continuous function, right? So we're looking for a point x such that f of x equals x, right? Can you tell me, like, okay. So can you tell me in terms of this graph, how can I find this point x? It has a geometric meaning. So if we look at the graph of this function right now, we can find out what is that point x where f of x would be equal to x. So the answer is, if we look at the line y equals x, this line, well, it goes through the origin, this line. There would be an intersection. There would be an intersection point. There would be a point. There is an intersection point. Which the line y equals x there has an intersection with our graph, our function, the function f of x. See, that's the point here. I claim the x here is that x which we're looking for. If you look at this x here, it has two properties. First of all, if you look at this point x on the graph, this point, the other component is f of x, right? Because it's a point on the function. But on the other hand, this point is also on the graph of the function y equals x. So here y, which is f of x, is equal to x. So the point which we're looking for, this fixed point, the point where f of x is equal to x, is always the point which the graph of the function at that point has intersection with the function y equals x. So the intersection of the graphs of these two functions is the point which we are looking for. Is it clear up to this point? Is there any question now? Okay, so if we understand this fact that a fixed point on a function is the intersection of the graph of the function with this line y equals x, then in order to show any function f which is continuous from 0 to 1 to itself, from this interval to itself, has a fixed point, in order to show that, we only need to show for any function from 0 to 1 to 0 to 1, from any function, doesn't matter what it is. If we look at this line y equals x, there is always there is an intersection point. Maybe it would be better to do it a little better. So this is a function f, any continuous function, and this is the line y equals x. And we want to say these two graphs, one is this line, the other one is the function, they always have some intersection point. It's not possible to, like, for these two graphs to miss each other. They're going to have an intersection point. That's what we should prove. Okay, and why is that true? So now that's what we want to prove. Why that's correct. Okay, I can probably erase here. Okay, so this is what we want to show. We want to show the graph of the function, graph of f, and the line y equals x. They always have some intersection. The intersection of these two things is always non-empty. There exists always a point x here. That's what we want to show. Okay. Okay, and the reason for that is, so we have y equals f of x. This is our function, and y equals x, the line. We want to say these two have intersection points. These two intersection means they're equal, right? Think about this new function. So I want to say at some point f of x would be equal to x, or equivalently, I want to say f of x minus x is going to be 0, right? If I take x to the other side, it means I want to show this equation holds. Now, let's call this f of x minus x. Let's just call it g of x. I define the function g of x to be f of x minus x. Let's see what is g of 0. Well, g, again, is a function which is defined, well, the domain is 0 to 1. We don't know what is the range, but it's a subset of R. Let's see what is g of 0. G of 0 is f of 0 minus 0, which is f of 0. But we already know f of 0, well, f is a function from the interval 0 to 1 to interval to 0 to 1. So this is a number in this interval, right? What is g of 1? G of 1 is f of 1 minus 1. Okay. Now, this is quite interesting because f of 0 you go, you should mute yourself, but I'm gonna do that for you. Okay. So, but f of 0 is this interval 0 to 1. So this is non-negative, right? It's either 0 or it's positive. So g of 0, which is equal to that, is greater or equal than 0. G of 0. And g of 1, which is f of 1 minus 1. What about this one? The point is that because f of 1 is a number between 0 and 1, it means f of 1 is between 1 and 0, right? So f of 1 minus 1 is between 0 minus 1, which is just minus 1, and 1 minus 1, which is 0. And this thing here is g of 1. Oh, I can't write there. I'm gonna continue here. So g of 1 is gonna be in this interval. As you can see, it is a non-positive number. It's not gonna be positive. So g of 1 is gonna be less or equal than 0. Now this is important because if you look at the definition of g one more time, g of x is f of x minus x. We assumed f is continuous. Well, f is continuous, x is of course continuous, and subtraction of two continuous functions is going to be continuous, so g is continuous. Now, g of 0 is greater or equal than 0. Now, there are two cases. Either g of 0 is equal to 0, this is one case, or g of 0 is positive, right? I mean, when we say something is greater or equal than 0, it means one case that might happen is that it is equal to 0. The other case that might happen is that it's gonna be positive, right? Now, I want to say in both of these two cases, we can prove our theorem. The reason is that if the first case happens, if g of 0 is equal to 0, it means, well, what was g? G was f. G was f of x minus x. So here, f of x is going to be f of 0 minus x is also 0. This is, well, 0. Therefore, f of 0 is 0. So we are done. We have that fixed point which we were looking for. So in the first case, when g of 0 is 0, f has a fixed point. And we're done. But what about the second case, where g of 0 is positive? Well, now in that case, we should look at the other point, g of 1, right? I mentioned, so we saw here above, we saw g of 1 is less or equal than 0. But again, being less or equal to 0, there are two different cases. Either g of 1 is equal to 0, or it's strictly less than 0. So we should consider both of these cases. So let's call them 2.1 and 2.2. So the first case is where g of 1 is equal to 0, and the second case is where g of 1 is less than 0. Now, if the first case happens, it means g of 1 is equal to 0. But remember, g of 1 is f of 1 minus 1. And this thing is equal to 0, means f of 1 is equal to 1. Again, f has a fixed point. There is a point x where f of x equals x. This is that fixed point. So again, here f has a fixed point. The only remaining case, is when g of 1 is strictly less than 0. Okay, so 2.2, it means we have this assumption here, g of 0 is strictly positive and g of 1 is strictly negative. This is the only remaining case. If we show the function f has fixed point in this case too, we have shown f has fixed point in every case. Therefore, f always has a fixed point. Now we have a continuous function g, which at some point it's positive. So this is the function at g, this is the graph of g. At 0, the function is positive. And g of 1 is negative. So g of 1 is going to be something negative. And this is the graph of g. Okay, can you tell me if we have a function, continuous function, which at some point it's positive, defined in an interval, which at some point it's positive, at some point it's negative. What is the important property of that function? Something definitely is gonna happen at some point. What is that? You can just raise your hand and tell me, or you can unmute yourself and tell me. So here we have a function g, continuous function g, which at some point it's positive, at some point it's negative. What can I say about g?
At some point, it's going to equal 0.
Yes, exactly. So if you have a function which is continuous and it's at some point it's positive, at some point it's negative, definitely it has to cross this line at some point. And exactly at that point, this function is going to be 0. So there exists a point x where the function g is going to be 0 there. But again, let's remember the definition of g. We defined g to be f of x minus x. So f of x minus x is 0. Well, it simply means f of x is equal to x. And Kyle, it doesn't necessarily imply that the function takes value on the interval g0, g1, because although that's the case in my graph, but the function might, rather than what I have here, it might look like this. So this is g0, for example. Say this is g of 1. So what you're saying is that the function will definitely going to be bounded by these two values, but that's not the case. So the function can go outside of these bounds. So if you look at these parts, they are not in that interval anymore. So it doesn't have to stay there. But I think you are also what you said, you kind of want to imply that 0 is in that interval. So anyway, the function is going to be 0 at some point, and at that point we have this property that f of x is going to be equal to x. So it's simply intuitively, well, if I want to just draw the graph again, it means if you look at the function f, since the function f is defined on this interval 0 to 1 to 0 to 1, as I said, the function has the function f. If you look at the graph of f, it has a fixed point whenever it has intersection with this line, y equals x. And intuitively, when you have a graph of a function going from, well, 0 to 1, at some point it has to cross this line, right? It can't jump over this line, right? It has to cross this line at some point. So that point is going to be the intersection point. Now, is there any question about this proof? This is a quite important theorem. The fact that any continuous function from an interval to itself, here we had the interval 0 to 1, but this specific interval doesn't matter. It could be 0 to 2 or whatever. The only important thing is that we should have exactly the same intervals in domain and range. They should be the same. Like if this is, rather than 0 to 1 is 0 to 4, this one should be also 0 to 4, and the theorem is gonna hold. And this is quite important theorem in math. Okay, any question here? Okay, so we can look at the second question. Okay, so the second question is about a function f being uniformly continuous. I want to say the function y equals x squared is, well, this function is obviously continuous. I want to say this is uniformly continuous on an interval, say 0 to 1, but it's not uniformly continuous on all of R. Do you know the definition of uniform continuity? Are you familiar with that? If you're not familiar with that, tell me so I would define for you what does it mean for a function to be uniformly continuous. If you are familiar with that, you can think about this problem for like 5 minutes or so. Oh yeah, so yeah, I can tell you the definition. So being continuous means, so if I have a function f from say a to b, or say from R to R, being continuous means for any point x, and for any positive epsilon, there exists a positive delta such that for any x prime, where x prime and x, the difference between x prime and x is less than delta, f of x prime and f of x, the difference between these two is less than epsilon. The order here is really important. And one other thing is that this point x is part of the definition. Now, when we say a function is uniformly continuous, a function f from R to R, it means for any positive epsilon, there exists a positive delta such that for any 2 points, where any 2 points, x and x prime, where x minus x prime, the absolute value of that, is less than delta, we are going to have f of x minus f of x prime is less than epsilon. Now, these two definitions, they look pretty similar, but they are really different. And the difference is that here in the first definition, we say for any x and for any epsilon, there exists a delta. This delta depends on two things. It depends on epsilon, but it also depends on the given point x. Delta is not independent of x. What I mean by that is that if, for example, this point x is 0, this delta is going to be something. If this point is another point 1, this delta is going to be something else. But in the second definition, this definition requires the function to have this property that for any epsilon, there exists a positive delta such that this thing is correct, this definition is correct for any point x and x prime. So this delta is now supposed to be independent of x. It doesn't depend on x anymore. So for a function to be uniformly continuous, it's a stronger property than being continuous. So if a function is continuous, it doesn't imply it is uniformly continuous. But if a function is uniformly continuous, it is definitely continuous. So now here we know y equals x squared is continuous. We want to show, if you think about y equals x squared as a function defined only on this interval, so it's gonna be, so y equals x squared. If we consider it as a function defined on 0 to 1 as the domain, the range is also gonna be 0 to 1. On this interval, we want to say this is uniformly continuous. And this is how y equals x squared looks like. This is the graph of the function. This is the interval 0 to 1. But although it's completely continuous, as you can see everywhere, we want to say it's not uniformly continuous. And again, intuitively, for a function to be uniformly continuous, it means the way its growth is kind of also bounded. It doesn't grow very, very fast. If a function grows very fast, it's not going to be uniformly continuous. So the function y equals x squared doesn't grow very fast on this interval, but as it keeps on, if you continue to look at the graph of the function, it's going to grow faster and faster. That's why it's not uniformly continuous. But we want to prove that. Okay, you can try to write down these two definitions, and well, especially the second one actually, and check if this function is uniformly continuous or not, or what do you think, for a few minutes. You can raise your hand if you have any question. You mean uniformly continuous by uniformly convergent? Yeah, the point is that as long as the interval you choose is closed and bounded, this is correct. So this is a theorem. If a function is continuous, so if you have a continuous function, if you have, let me write the theorem here. If you have a continuous function, and if the domain is, closed and bounded, then the function is uniformly continuous. So here, what's important about this interval 0 to 1 is that it's closed and it's bounded. And the function y equals x squared is continuous. So in this case, if it wasn't closed, that would have been still uniformly bounded. But anyway, this is an important theorem which we would be able to prove it. It's not very hard. Okay, let me erase some of these things. Is the definition clear? Do you understand how? So raise your hand if you're still confused. This is quite confusing concept because the definition really looks like continuity. They don't look very different. The difference is quite subtle, but they really are. There is a difference. And so some functions are continuous, but they are not uniformly continuous. So again, one more time. So function bounded continuous on closed interval is the same as uniform continuity. No, it's not both ways. And so if a function is uniformly well, I mean, the way you wrote it is not exactly logically correct, but I think you are understanding what I mean. Yes. So yeah, so maybe I can summarize everything I said. So let me erase everything actually. So yeah, so we have a concept of continuous function, continuity, and we have a concept of being uniformly continuous. So as I said, uniformly continuous implies continuous, but not the other way around. And the way to go from continuous to uniformly continuous, we need some extra assumptions. One of them, which is quite important, is when the domain, as I said, is closed and bounded. It is about the domain, not the function itself. So the function itself doesn't have to be bounded, but actually this is a corollary. So if domain is both closed and bounded, the function f itself also becomes bounded. So that's also correct. But the other way around is not correct. A function can be uniformly continuous, but not bounded. For example, y equals x as a function from R to R. It is uniformly continuous, but of course it's not bounded. And there is nothing wrong with that. So this thing, as you mentioned, is sufficient. But as this example shows, not necessary. Okay, let's look at this specific example we have here. It might be enlightening. So we have this function y equals x squared from the interval 0 to 1 to the interval 0 to 1. And we want to say this function is uniformly continuous. So uniformly continuous means for any epsilon positive, there exists a delta, a positive delta, such that if for any 2 points, x and x prime in domain, here the domain is the interval 0, 1. If 2 points are in domain, if their difference is less than delta, then that would imply f of x minus f of x prime is less than epsilon, right? So we want to prove that. So the way to prove it is that we should assume a positive epsilon is given. So a positive epsilon is given. This is given. In order to prove this, we should find positive delta such that this delta and this epsilon, they would satisfy everything we wrote here. So we want if x and x prime are closer than delta, f of x minus f of x prime, they would be closer than epsilon. But because f is x squared, f of x is x squared, and f of x prime is x prime squared. We want this thing to be less than epsilon. That's what we want to happen. We know x squared minus x prime squared is equal to x minus x prime times x plus x prime, right? So in order to make this thing smaller than epsilon, we can make this thing smaller than epsilon. But x minus x prime, and this thing is equal to x minus x prime times x plus x prime. But this thing, x plus x prime, it's bounded itself. X plus x prime is always less than a certain specific number. What is that number? Just in order to make sure you are listening, someone tell me what is the bound for this thing. X plus x prime is always less than a given number. 2, yeah, of course. Because both of these numbers are between, yeah, thank you, both. Both of these numbers are between 0 and 1, so their sum is, of course, less than 2. So the whole thing here is going to be less than x minus x prime times 2. Now, I want to make this thing smaller than epsilon, but this thing itself is less than this one. So if I make this one smaller than epsilon, of course, this is going to be smaller than epsilon too. And it means x minus x prime has to be smaller than epsilon over 2. And this is exactly what we were looking for. See, look at the definition. We wanted to find some delta such that if x minus x prime is less than that delta, everything works well. Delta is kind of given here. You can see that it's naturally, it's telling us x minus x prime should be less than epsilon over. So we were looking for delta. Delta should be this number, epsilon over 2. If delta is epsilon over 2, then everything works. And therefore the function is uniformly continuous. It might be a little confusing the first time you see this thing. You should try a few different examples. Yeah, so maybe let's try to see why it's not. So this is an example of a uniformly continuous function. Now we can look at the case where we're looking at the function y equals x squared from R to R, like the whole real line, and see why it's not uniformly continuous there. That might be also helpful. So any question here? Okay. So we want to see that the function y equals x squared is a function from R to R is not uniformly continuous. Okay, so, well, maybe it's better for me to write it. We don't have much time. So the proof is, so we have proof by contradiction. What it means is that suppose suppose this function x squared from R to R, suppose is it is uniformly continuous, right? So for any epsilon, there exists some delta, which delta depends on epsilon, but it doesn't depend on x. So delta only depends on epsilon. Maybe I can show it with delta sub epsilon, so we understand this delta depends on epsilon. It's just a notation, it really doesn't matter. Such that for any 2 points, x and x prime, which they're closer, their difference is less than delta epsilon, the value of f for these two is less than epsilon. Okay. So let's rewrite this thing. As we know, f is x squared, so this is just x squared minus x prime squared. This is supposed to be less than epsilon, and we know this is x minus x prime times x plus x prime. This is supposed to be less than epsilon, right? So it's supposed to be correct for any 2 points, x and x prime, where their difference is less than this, right? So for example, if x prime is, so for example, if x prime is x plus this delta over 2, the theorem should be correct for these 2 points, x prime and x, because x prime, if x prime is x plus delta over 2, then x prime minus x is delta over 2, which is less than delta. So f of these 2 points should satisfy this property. So so x squared minus x prime squared, which is x plus delta over 2 squared, should be less than epsilon. Is it clear up to this point? So I'm assuming the function is uniformly continuous. I want to get to a contradiction, right? The definition says whenever we have 2 points which are closer than delta, the values of their functions should be closer than epsilon. I'm saying being closer than delta, for example, that's an example for that. If x prime is x plus delta over 2, these 2 points, they satisfy this condition. So this thing should be correct for them. Okay. So let's expand this thing. It's x squared minus x squared plus delta squared over 4 plus 2x delta. This should be less than epsilon. And if we consider this negative sign, these two would cancel. So this is the same as saying delta squared over 4 plus 2x delta is going to be always less than epsilon. And this is the point which we understand what's the difference between uniformly continuous and continuous. This thing should be correct for any x in domain. For any x in domain. Is it correct for any x in domain? Just look at what we have there. We want to say the absolute value of epsilon squared over 4 plus 2x delta is less than epsilon. And it says it's correct, doesn't matter what is x. Of course it's wrong. I mean, just take epsilon to be 1 billion. Of course, 2 times 1 billion times delta, blah, blah, plus something else is not going to be less than epsilon. there is no bound on x. We can make this x larger and larger. It can be any point in domain, and domain is not bounded. Therefore, we can make this x larger and larger. And of course, this thing times something else plus another positive number is not going to be smaller than epsilon. Of course, this is not correct. So this is not correct. So this is where we see how domain being bounded affects the problem. If domain was the interval 0 to 1, this x had to be in that interval between 0 and 1, and we had a chance of proving 2 times x times delta plus delta squared over 4 is less than some epsilon, because x is itself a number between 0 and 1. But here there is no bound on x. We can send x to infinity. And of course, if we send x to, say, infinity, of course this thing would go to infinity and it's not less than epsilon. Any question? Okay, just I'm not 100% sure about the quality of my voice, or if there is any delay. Also, if there is any technical problem, it's a good time to tell me now. Or if everything is okay, tell me it's okay. Okay, it looks fine. Okay, thank you. Okay, we would continue next week then, if there is no question. Is there any question? Okay, I would upload this video on Blackboard so you can look at it later. Also, I'm going to be online during my office hours and MLC hours. I'm going to be online on Zoom, and you can see you can now see my my account, which is just my first name and my last name. I'm going to be online on Zoom. So if you have any question, you can just come here and we can chat and we can solve your questions. Okay, that's it then. Stay safe, and I hope you can study well. Okay, bye.